Welcome to myprojectbazaar.com. Our product title is Multiple Cell Reference Scheme for Narrow Reference Resistance Distribution in Deep Submicrometer STT-RAM. Let us see about abstract of our product. Spin transfer torque random access memory is called as STT-RAM. It has received increasing attention because of its attractive features such as good scalability, zero standby power and non-volatility and radiation hardness. The use of STT-RAM technology in the last level on chip caches has been proposed as it minimizes cache leakage power with technology scaling down. Then identify key optimization that can be employed to improve its characteristics. This design lower the retention time by reducing the planar area of the cell, thereby reducing the write current. Logic and large lost level caches are frequently used to bridge the performance and power gap between processor and memory. Although traditional processors implement caches as SRAMs, technologies such as STT-RAM and MRAM and it has high write latency and write energy consumption is high. In this proposed implementation is 18 cross 16 multiple cell reference scheme on single STT-RAM. This CMOS design is simulated in Tanner EDA tool. Next we see about flow diagram of our product. This is our flow diagram. In this flow diagram having several blocks. First one, input logic and inverter. In that block the input is given as a logic format and that input logic is fit into a inverter section. In that inverter section is a CMOS technology based inverter, that is one NMOS and PMOS is connected in a structural manner. After that the data will be given into the write logic. In the write logic is used to write the operation to the overall blocks. After that the written data will be sent to the multiple cell reference block. In that multiple cell reference block is 18 cross 16 multiple cell reference. After that the data is fed into read logic. In the read logic is used to read the data in that blocks. After that the data is fed into output logic and inverter block. In that block the inverter is used to get the output value from the logical format. Generally in case of the MRR scheme with the disturbance free reference scheme, each state of the reference cell is fixed and not changeable after fabrication. In the 16 CR scheme, however, each state of the reference cell needs to be changeable to implement a reference balancing scheme to balance state 0 and 1. For correct write operation of the reference cells, two SLDRVs are used. When the first reference MDJ at far left is connected to PL0 to be written to RL PL0 is connected to VDD through the PLDRV block, then the output will be getting the output logic and inverter blocks. Next we see about running process of our product. In this proposed implementation is done in Tanner EDA tool in the CMOS technology. First to open the Tanner tool SEdit window. Open that SEdit window, then create a new cell view. After creating the new cell design, we click the corresponding library files and model files. After selected that, we create the circuit as per the base paper. After creating the circuit, we click the run icon. After clicking that, the T-Space window will be open. In the T-Space window, the corresponding run time and also system on time will be shown in the corresponding window. This is the T-Space window. In the T-Space window, overall time step and setup timing and transient analysis time, overhead time and total system time will be shown. The overall system time is 4.25 seconds. After that, the corresponding WEdit window will be open. In the WEdit window, the output data will be shown in the waveform format. So in that waveform format, this is the corresponding output waveform. This is overall output. If you want to expand that, click the expand chart, then the output data will be shown in like this. This is input data PLDRV voltage. The x-axis is time and y-axis is voltage in the unit of volt, and the x-axis time is unit of nanoseconds. The overall time is 600 nanoseconds. This is output of the corresponding VSA. This is output is getting from the multiplexer, and this is output logic and inverter block outputs. This is SLDRVA and SLDRVB output datas. And if you want to corresponding data's frequency value, then click the FFT value, then corresponding voltage and frequency values are shown in here. The overall frequency is 500 megahertz, and this voltage will be shown in the decibel value. So this is the W edit window. Then this is T-space window. In the T-space window, and another data is overall elements requirements data, and which amount of elements we use in the overall circuit. Which amount of means how much NMOS and PMOS we use for this designing, and how much voltage source we used in this designing. And this T-space window is used to help the overall power consumption calculation. So the power consumption value is shown in the T-space window. This is overall power consumption value. The x-axis is power in the unit of microwatts, and this is the overall voltage input and output data. So this is power consumption value. The power consumption is around 40 microwatts, that means 0.004 milliwatts. If you want to expand that, so click the expand chart. The corresponding output will be displayed in the expanded format. Thank you for watching this video.